Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about femtosecond lasers. So let's dive deep into it. So this femtosecond laser is basically a laser pulsed system. Even though to our eyes it will look like a continuous laser, because again even the gaps between on and off is not that much. Basically it's a the frequency, it could be high as kilohertz or sometimes as high as megahertz. So from our point of view it will look like a continuous laser beam. However, if you start to measure the pulse width, yeah, this is where it becomes ludicrously tiny. How tiny? 10 to the power minus 15 second. So we start with a nanosecond. That's fast. That's like 10 to the minus 9 second. Then you come to picosecond. Then it becomes 10 to the minus 12. Then you come to femtosecond. That puppy is 10 to the minus 15 second. So we are talking ultra tiny short pulse. And this is such a short pulse that power amplification becomes stupid, meaning you are taking the energy and compressing it like and when you compress it, the energy level goes ludicrous. Even though you are only dumping 1 kilowatt or maybe 2 kilowatt, the output power reaches terawatt power level. Let that be very clear. It's basically in school you know transformer it's a very linear device. So you have voltage and basically amps, and if one gets exchanged for the other, there is other option also, temporary compress it. So femtosecond laser does that. So basically even though input energy could be very small, the oomph that is dumping into the pulse could be idiotically high. So terawatt level power. And how fast it is, what kind of time frame we are talking about. It is so fast that things can't even react, meaning you're drilling with let's say even a picosecond laser or nanosecond laser, it will react. It's like, oh, you're dumping laser, I'm getting hot, things are happening. And if you worked with laser cutters, they will tell you that sheet metals are not very good for you because it warps from the heat. So you could try to do it with nanosecond laser, but it still will have some effect. But when you go to picosecond, it's like femtosecond is like, nope, it just nopes it. The material gets drilled before the material has time to react. So even under electron microscope, it's a clean hole. So for our eyes it will look clean, but that is electron microscope clean. So that's the whole consequence of being so short a duration, meaning the material, literally you can laser drill everything and you can put it in your hand will not burn, because it, like, there was not enough time for material to react, so to say. It's so goddamn fast. So this is what we are talking about, femtosecond laser. So how the heck we reach this? Because be mindful, while we are talking about femtosecond laser, it's not like it's 1 pulse per hour. It's like in kilohertz or megahertz. So femtosecond is two things. It's a very short and very fast. It's original Fast and Furious. So how wide this system is in time is it's a basically diameter of a virus. Like same way you measure distance in light year, if you take a light beam, it travels only distance of a virus in 1 femtosecond. So it's a width of a virus. And in terms of frequency, you want to get some idea. While switching frequency could be low, the actual pulse width would be 100,000 terahertz. So yeah. So it starts with 100 terahertz to goes up to 300 terahertz. So this puppy is fast, like bonkersly fast. Like gigahertz is slow to it, and it's not even 1 terahertz. It's like 100 plus terahertz. So it's very, very fast thing that we are talking about. So how the heck we are achieving this magical thing? We are tricking light into doing it. We call it mode locking, is the driving principle. If you want to understand that, you have to dive deep into mode locking. Now, what is that? Well, you have to understand, whenever you look into electronic circuit, while modern electronics are fast, like gigahertz switching is possible. To be fair, power electronics only do like megahertz, and that's also nowadays. You can't even expect anything touching a few gigahertz, like 10 gigahertz, like you can't expect that. The moment you go into like faster than that, like 1 terahertz, yeah, no. So femtosecond is not possible. So what we do is first understand that there is no trick, not even in future, that most likely will work, where it's like, okay, I can switch it that fast. No, you can't. So what we do is basically unlock mathematics of constructive and destructive waveforms. Meaning, if you have a cavity, a mirror here, and this cavity has waves, standing waves, and waves will cancel out in one direction and it will amplify in another direction. So basically you'll have standing wave and they will constructively add up, destructively destruct in one place. So the amplitude goes up. But here's the, this is a very simplified example. You have two waves, but what if you have multiple waves? What if you have 1, 2, 3, 4, 5, 6 in real world scenario, 50, 60 or maybe 80 wavelengths that are going back and forth? Then you can reach a very unique property which we call Modelocking. We are not doing it, is more like we are extracting this feature out of it. So once you have this collectively done properly lasing, you could literally reach a scenario where majority of the light is cancelled out, that energy is gone, but where it's gone, well, where it's constructively being created. That point will be, penalty would be it's a bit wider, like in terms of laser continuous is generally pure monochromatic. It's like almost absolute, even if you have like a spread it out, it's almost absolute monochromatic. Here, because you have collapsed so many wavefronts, it is a bit sloppy. Now again, it's not white, it's not super continuum laser, but it has a bit more component. It's not as tight, so to say, but pulse wise it's like ludicrously tight. So this is how we achieve it, and that's how we can successfully make 100 terahertz plus. So basically pulse width is like 100 terahertz. So this is very fast pulse that we are doing. And again, we are not directly doing it. You cannot do it. You just create a cavity that oscillates like that, where it creates a certain level of feedback loop and certain levels of standing waves that creates this unique circumstance. It's more of a material property, less of a like, we want this to happen. So it's a clever trick, very clever trick. So how do we create this? Well, if you really want to do something serious damage, like if you want to like have a ceramic that like if you touch it wrong, it shatters and you want to drill through it, it's like, I got you fam. So if you want to do that, Modelocking, basically femtosecond laser is your starting point. So you will have short pulse laser, which will be femtosecond laser. How would you do it? Well, you will use Kerr lens, K-E-R-R, Kerr lens. This gain medium has unique property that will allow you to achieve this. Or there is another option, especially if you are dealing with fiber laser as a source, you can have saturatable absorber. That will basically, these are things are acting in such a way where they are, unless light is high intensity enough, it will not pass through. So it's just like, it's just eating it up. If it's not bright enough, it's not amplifying it. So it's like forcing light to behave in a certain way. So again, saturatable absorber and a Kerr lens, you can choose one, or sometimes may even combine both of them to give you the ability to create femtosecond laser. Now, okay, if you have femtosecond laser, problem solved? Well, no, it is good enough, powerful enough to do LASIK surgery, but it's not good enough to touch metals. Like if you touch ceramic is like, oh, are you trying to do something? Tickle me to death. So you can't do that. But so here's the deal. People try to, okay, we have femtosecond, what if we send it through an amplifier? Yeah, amplifier blew up. Because again, it's the temporal compression is too goddamn high. So we take it, we stretch the space time of it. So basically, if it's a 2 millimeter width, we stretch the space of it. So it's a 2 millimeter, 20 millimeter. Cool, awesome, GG. And then we stretch the time out of it. And you're like, wait a minute, how can we expand the time? Well, if you remember your high school physics, you know this. A prism. If you understand this correctly, you understand the fact that white light has a mixture of wavelength, exactly like femtosecond laser. Now, if you send it through a prism will fold the light, basically force the longer pathway to happen on the same beam. So beam is the same, it's coming same, but it's bending based on the wavelength. So blue light will bend a lot, so it will come out. Red will not bend a lot. So not only you are physically expanding it, you are also temporally delaying it. So meaning this beam will exit first, this will exit later, because again, time is off. Femtosecond is that slow, a lot fast. In femtosecond, this is like in a continuous laser, it will not make sense. In femtosecond, it will make a difference. So that's why I specified light only travels a width of a virus. So from that point of view, it's like, whoa. So instead of like super sharp, you whoa. So basically you unpack the briefcase. You take the briefcase, you unpack the briefcase. And then you stretch it via two things. If it's low energy, you can do it with prism. If it's high energy, you can't do it with prism, because again, refraction going through the material, it will destroy the material. So you have to do diffraction grating, because that's the reflection, much more efficient at high energy. And again, non-self-destructing at high energy. So that way you reflect it, basically spread out the space and time continuum of it. And after that, you send it to amplify state. Because it's now stretched, it can go through amplification safely without catching on fire. And what amplification material? People did try some optical fiber materials that we use for laser communication, basically optical communications. It catches on fire. So we have to use titanium sapphire crystal. Now again, there are certain other mediums also, but this is one of the most common or popular, I would say. So titanium sapphire crystal. Here you dump energy into it, photon-based energy, and that just takes your opened up briefcase. It puts a lot of energy. So basically the briefcase came in, it was 1 kilogram. You opened the briefcase, you dumped 100 kilograms into it, packed the briefcase up. So now you have really fat, powerful pulse. But again, it's not femtosecond. At this point, it's a basic laser. It's like, who cares? But here's it to oomph it up. So put energy into it, you pack the briefcase again. So how do you do it? Exact same thing how you expanded it. Basically put a different prism that is folding it backwards. That's what we call compression stretch. So you stretch it, then compress it, and then you have ultra intense, super duper, hyper high power laser pulse. Like at that point in time, like zirconium is like, it's like, bro, I can't deal with this. Zirconium, doing, it just drills through it. Like, I don't care. I don't care, you are the hardest material. I have zirconium teeth. So it's like, it does not care. It's like, zirconium is so strong, like most drill bits will like attack with it. It's like, bro. So this is the construction of it. You start with the pulse and then you unpack it, pump a lot of energy into it, repackage it in space and time, and then let the laser serve begin. And mode locking is the core aspect of it. And do not think in this way like we are tuning it, we are doing it, we are sending multiple waves. It's not that complex. It's more of like clever utilization. There are certain feedback loop mechanism, and sometimes you can have feedback loop in this stage where you can tune the laser outputs, so to say. Basically, once the laser has been expanded, it is easy enough where you can have like a slit physically blocking the wavelength, and then you can tune it like this and that. So there are certain mechanism where you can add on top of this to get far more control, although not necessary. If especially as a drill system, you will design it to be maximum power efficient at maximum one wavelength, and the end, go home sweet dreams. So that's the construction of this ultra powerful laser. So let's understand some history of the laser so we get some context of it. In 1960s and 70s, we started with this puppy. Basically, a flash lamp, ruby rod, and voila, laser was invented, and things got heated after that. So in 1974, we started to understand the principle of mode locking. I specified mode locking is not what we are doing. It's more of like a property of a material. And it's like, we can do it. So at that point in time, picosecond laser demo was done. So people are like, okay, we see you. Temporal compression became, instead of theoretical paper, to like, we can actually do it. So things got interesting. And in 1980s, people figured out titanium sapphire mode locking system. And at that point in time, femtosecond laser was born. And true femtosecond. On paper, people figured it out that it should be doable in 1974, but it took till 1980s for people to like, okay, we have a femtosecond laser. And after that, in 1990s, that chirped pulse amplification was basically unpacking the briefcase, putting a lot of bricks into the briefcase, folding the briefcase, and throwing the briefcase. So that chirped pulse amplification. At this point, laser became powerful enough where you can do things that was unimaginable. Basically, we knew we can do things with drills, basically lasers, but there was like, if we put enough power, it's not short enough pulse, it will cause thermal destruction to the material. So we knew what we needed to do, but we just did not the oomph. This technology solved the oomph problem. So that happened in 1990s, and it was such a big deal in a high energy physics that in 2018 Nobel Prize was given for this gentlewoman crew to give the whole boost to field of lasers. So as of now, this is the highest laser energy we have. And 2001, this new milestone was opened, basically femtosecond LASIK. Now, they generally do not call it that. They generally call it blade-less LASIK. We had lasers, but again, you still had to have some cutting actions going on. So femtosecond allows you to bypass that issue also. So femtosecond. Now, this was done in 2001. Be mindful, laser surgery was done before that also. But in 2001, femtosecond laser was used. And this time, they were utilizing 1053 nanometer, basically infrared laser to do this bidding. Now, in 2010s, commercial users started to expand because at that point in time, this technology of 1990s was mature enough. People are like, hey, we can drill things. Because before that, we were relying too much on an electron beam and this and that. Now, we are like, hey, we can just laser it. We can just like we can just laser it. So that became a thing. And by 2010s, commercial use expanded, meaning you can just pick up a phone and buy the piece, meaning I can buy it. Assuming you have a deep enough pocket, you can buy it. It just became a normal thing rather than like, flagship product that Boeing has, Lockheed Martin has, NASA has. No, it's like you have a money, buy it, take it and go. So that began. And this was utilized for micro machining and surface structuring. These were the two most we could not do it other ways. There were other things also. One of my personal favorite example was that mold. The mold, if you want to make out like plastic injection mold, you generally want to have very hard steel, like ludicrously hard steel. Now you do your best with EDM to give you the best finish and all that. But here's the deal: if you want to give it texture, like I want to make this physical part reflect like it's a carbon fiber, that requires micro machining. EDM, while it is good, not that good. Like especially on a complex surface, is like not that good. So femtosecond laser is like, I got you, fam. It literally goes there edges. Like I've seen some molds which literally have carbon fiber imprinted to them, and if you take the mold out of it, do plastic injection, it literally looks and feels like a carbon fiber part, because it's, on a microscopic level, it has the same structure. So, and again, those things are very hard, and it has to be precise. It has to be non-destructive. You cannot just dump a lot of energy. EDM will dump enough energy to cause issues. So fundamentally, those sort of things became possible. Before that, it was like a hell lot of a hassle to do so. Now it's like easy. Easy if you have deep pockets. And by 2020s, two technologies got together in the bed. Basically, femtosecond laser got together with high-speed galvos, meaning these galvo mirrors started to move much higher frequency, meaning now the surface area where you can do your stuff started to expand. So, or you can just do a lot of things very quickly. So you can have like, okay, I want to weld this ceramic insert to this stuff. It's like, I got you. Super quick, easy, barely an inconvenience. So all these things happened surprisingly quickly, given the fact that it only started in 70s. There are people alive from 70s. So, damn. So what can we expect in the future? Well, the reality is you have to know this is core level development. This is one of the development where physics is so far ahead that engineering has not caught up to it. So it's a core development in laser physics. Another aspect is it allows us to create what we call octosecond light pulse. Now, how fast is octosecond? Well, octosecond is so fast that electron cannot move fast enough. Electron going from here to here, it's like, bro, I'm taking time. Bro, relax. Why are you so hurry? Relax. Electron will say that. That's octosecond. I have no idea. I tried to understand the paper. My brain was like, nope. So, but it is possible because of femtosecond. And then you have bladeless eye surgery. That's why one of our commenter wanted to ask. But again, that's a medical thing, so I did not want to go too deep into it. Then you have my personal favorite, cold abrasion of hard materials. Basically, there are certain materials that are ultra duper hyper hard. We want to make stuff out of it, but the moment we touch machining to it, it's like, push, it shatters. So it's like, what can we do? Femtosecond laser, I got you, fam. I got you, fam. Now, my personal favorite is internal modification on transparent stuff. Like there are materials like Zuradar or some other crystals that are super duper hard, and doing things inside it without causing any issue to it is difficult. Femtosecond laser is like, I got you. I got you. My personal favorite, Microsoft Project Silica. I've already made a detailed video about this. This is the only technology I've seen that has some potential of surviving thousands of years, because it's a pure glass crystal. Now, let that be very clear, not soda lime glass. Soda lime glass is a very fragile glass. This is pure crystal. So it's hard. Like it will require you to have 1000 degrees Celsius plus temperature for a very long duration for it to melt. So it can handle that without an issue. You can put it in acid or anything. It does not care. It's like, bro, I got this. So it's a really good medium. But here's the deal. How the heck you put enough data inside it? Femtosecond laser is 5D voxel storage. Now it's like, wait a minute. What is fifth dimension here? Time travel? No, 5D simply means X, Y, Z, and 2 dimensions are from the femtosecond laser. So how wide the pulse is, basically it's etching. This polarization is etching the how long the pulse is. Long as in like physical dimension, like how long that width is, pulse width, so to say. And second, polarization. What is the rotational axis? So if the point is this big, it's 1 bit. Is this bit, different bit. Is this bit, different bit. So that's the 1 dimension, basically 4th dimension. 5th dimension is the polarization. That's why they are showing this like tuk, 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 tuk. And then you can pack like few 100 terabytes in one glass disk, and you do not have to worry about magnetism or anything like that. Like just put it and forget. So I really like that technology. But again, would not even be possible unless you had femtosecond laser. So there is a lot of amazing things yet to come with this femtosecond laser. Like we're just getting started. I really like the idea. Like, oh, we're just temporarily expanding it. It's like, what the hell? When the heck we started controlling space time? It's like light is easy to do with space time continuum controller. So cool stuff. So this was my presentation about basically femtosecond laser. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me disappointment. Please leave a comment because I do, try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.